In this video, we're going to talk more about logarithms. In fact, this is the last video lecture on logarithms. We're just going to spend this time to kind of wrap it up using transformations to help us graph logarithmic functions. And this is a very nice kind of roundup of previous topics anyway. A little preview of what we're going to be doing. It's exactly what the title implies here, is that we're going to graph logarithmic functions using only transformations. And a few things we need to know beforehand is that you need to know everything about exponential and logarithmic functions up to this point. Everything, basically, about logarithmic and exponential functions. You'll have to know about inverse functions, and you'll also have to know how to graph a function based on transformations. In other words, if I give you a base graph, you should be able to manipulate that to attain some modified version of the graph using transformations. So let's start with a simple logarithmic function, y equals log of 2x. That's log base 10 because the 10 is not written in there. Now, there's a couple ways to actually graph this using transformations, and that's the case usually with most logarithmic functions. One thing you should note is that the base logarithmic function looks like the following. And notice that this is, I'm just graphing y equals log base 10 of x. All logarithmic functions go through the point 1, 0. That's how all logarithmic base functions act. So as long as it's log base 10 of x, or log base 2 of x, or log base 115,000 of x, they all go through the point 1, 0. And then, to find out another point they go through, use the base. In this case, we have log base 10, so that means when you plug in 10 for x, the output will be 1. If this is a log base 2 logarithm, then we plug in 2 for x and we get out 1. And finally, next to finally actually, we have a vertical asymptote at x equals 0, because recall that you cannot plug 0 in for x into the base logarithmic function. Also note that the domain is all positive, and note the range is all real numbers. And now the final thing I want you to note here is that this is a logarithm base 10. If your base is greater than 1, just like with an exponential function, it is an increasing function. So notice this is an increasing function because as I look from left to right, the function values are climbing ever so slowly. Actually, it's very logarithms climb very, very slowly after x equals 1, but they still climb. It'll still go on forever. It'll eventually get to a height of 1,000, for example, but it takes a long time to get there. So this is our base graph. Now remember that I want to graph y equals log base 10 of 2x. There's two ways to approach this. Either we could take a look at the inside here and notice that when we're multiplying the inside, recall from base graphs and transformations, anything that happens on the inside of the function implies we're doing things horizontally. Anything that happens on the outside of a function, so if there was something out here or out here, that would imply that we're doing things vertically. So we're applying vertical transformation. So since that 2 is on the inside of our function there, this means that we have some type of horizontal transformation, either a horizontal reflection about the y-axis, or a horizontal shift left-right, or a horizontal compression or expansion. Well, if you're multiplying, it implies a horizontal compression or expansion. So just recall that f of ax looks just like f of x, except it has been, and then one of two things will happen. Either it's stretched or compressed. So we'll write stretched horizontally or compressed horizontally. And we have to figure out by what factor. Well, the factor will always be the value of a. So by a factor of a, of a. So in either case, you could say the same thing. It's just that to determine which one we apply just depends on the value of a here. Oh, and recall that when we talked about transformations, we said whatever happens to the inside of the function is opposite of what you would think. So if there was a plus happening on the inside of this function, like a plus 3, instead of moving to the right 3 units, it actually moves to the left 3 units. It does the opposite of what you would think. So instead of actually stretching or compressing by a factor of a, it's actually stretching or compressing by a factor of 1 over a. It's the multiplicative inverse. Okay, so in this case, if a is between 0 and 1, then we are going to be stretching. If a is between 0 and 1. So that's kind of opposite of what we would think. We would normally think that if this number right here is like 0.1, in other words 1/10, that we are going to shrink or compress things by a factor of 1/10. But actually, that actually stretches them by the factor that's reciprocal of 1/10, or in other words 10. So, and on the other hand, it will actually compress it horizontally by 1 over a if a is greater than 1. So what is happening in this case, again, we're on the inside of our function here. What's happening in this case is that this is going to be, since this number is greater than 1, this is going to be a compression horizontally. So it's compressed horizontally. Oops, I'll just write compressed horizontally by a factor of 1/2. In other words, all the x values that existed on this graph before are 1/2 of what they were. Let's see what that looks like. So what we do is we start with our base graph here, and we're going to compress it horizontally. In other words, all these x values are going to get closer to the x-axis by a factor of 1/2. So let me go ahead and hop over to show you what I'm talking about here. So we're going to compress all the x values by a factor of 1/2. So let's go ahead and do that. So notice that I erased out the old values that we had written in there. This point to the rightmost red point was 10, 1. But because we're compressing everything horizontally by a half, that point will be compressed to half of that 10, 1. It will now be, the x value will now be 5. So this point right here will occur at 5, but the y value hasn't changed. It's still 1. And before, this x value where we cross the x-axis was 1, and the y value was 0. Well, now, because we're compressing everything horizontally, the x value is going to be 1/2, since that's half of 1, and the y value is still 0. The y values don't change with horizontal compressions. Now, if I had a bunch of other points, I would also include those points in this. I could have graphed several more points, but I'm not going to bother doing that. One thing I do want to say is that if you look at the x values for all the other points that are on this graph, like let's say this x value right here, what I want to do is move that point to half of its x value, which will just be a little closer to the vertical asymptote. So all these x values that are along this curve here will get just a little bit closer to the vertical asymptote. They'll never touch the vertical asymptote, they just get a little bit closer. And that would be our graph of y equals log base 10 of 2x. Notice it doesn't look that much different than log base 10 of x. You can check this by using a graphing calculator if you want to. Just go over here, clear out any old graphs, and type in log of x and log of 2x. You'll be able to see that these are almost the same function, actually. So it does make sense that these will graph like that. I'm going to change my window a little bit and to match it up with the window that you see here. This basically goes from -10 to 20 in the x direction, and in the y direction the same thing, but it'll be very difficult to see. There's log of x and here's log of 2x. Notice it's exactly what I have graphed here. Very hard to see. If you want to adjust your window, you can. You know that the x values will never be negative, so I could do that. And it looks as though the y values don't really grow past maybe the height of 2 or something like that. So they do grow beyond that height, but it takes a long time to do it. But even then, in that very, very tight window, you still see they're kind of hugging each other. So we did a great graphing job. But I had mentioned that there was another way to graph that function y equals log of 2x. You could use the properties of logarithms to write log of 2x as log of 2 plus log of x. All I'm doing is saying I have two objects multiplying on the inside of the function means that I could break it apart to an addition. And really, to kind of show you how this looks, I'm going to say that's the same thing as saying y equals our function, our base function, plus some number. Now, this number just happens to be a log of 2, but if you put that in a calculator, it's just some number. So what this is saying is this function looks like log of x. So it looks like log of x, but shifted up. Because notice this addition is happening to the outside of our function, and as we mentioned, anything that happens on the outside of the function does things vertically. So this is going to look like log of x, but shifted up by this many units, log of 2 units. Now that's a little bit difficult to plot out, but if you look at our graph over here, it does look like the black curve, but shifted up slightly. And it is actually shifted up by log of 2 units. So that's another way you could do it. And to show you that this is true, you could just use your graphing calculator, again, to compare log of 2x. Let me clear these out. Let's compare log of 2x to log of x. So log of x plus log of 2. And when I graph that second curve, I'm going to go ahead and show you the graphing. Notice I've hopped over, my cursor's blinking on the line. If I hit enter a few times, it changes how the line is graphed. So I'm going to use that one. What it's going to do is trace out the curve. It makes it a little bit easier to see. I'm going to adjust my window to go from 0 to, let's just go from 0 to 10. And our y minimum will go from -1 to 1.5. So the first curve that'll graph is log of 2x. The second curve that'll graph is log of x plus log of 2. Here's log of 2x, and now you're about to see there's log of x plus log of 2. Notice that as it traces it out, it actually is tracing out the same exact curve, very slowly for some reason, but it's tracing out the same curve. So they are the same function. The curves represent the same thing. Now let's go ahead and graph log base 3 of 1 over x. This 1 over x on the inside of our function really does make this kind of a hard function to graph if it was any other function in the world. But the fact that this is a logarithm means that we can actually manipulate this a little bit. This is log base 3 of x to the -1. And I know that logarithms allow me to unlock exponents. I have a property that says I can grab that exponent and throw it out in front of this logarithm. So I'll go ahead and rewrite this one last time. In reality, I'm being asked to graph a negative log base 3 of x, which actually is a little bit easier to graph. This is just going to be, well, since that negative is on the outside of the function, it's going to be a vertical reflection about the x-axis. And then otherwise, it's just log base 3 of x. Now recall, this was the original graph that we're dealing with for the log base 10 of x, but let me adjust this so that it becomes the log base 3 of x. So notice the manipulation here, log base 3 of x. All I did, remember all logarithms go through, base logarithms that is, go through the point 1, 0. So that didn't change. Then I just said, well, since I'm log base 3, if I plugged in 3, log base 3 of 3 would be 1. So In other words, when x is 3, y is 1. If I plugged in 9, log base 3 of 9, well, that would be 2. Okay. And then the next one that I could possibly do would be 27. Log base 3 of 27 would be 3. So it's kind of off my screen. So I'm just going to say that it slowly rises up. It'll eventually hit a height of 3, but that'll be eventually. But otherwise, this is basically the graph of log base 3. And what I want to graph is, a negative log base 3. So I'll just go ahead and draw on that same graph the negative log base 3 of x. To do that, I'll go ahead and start plotting points. Maybe I'll use green. And remember, negative log base 3 of x means all the y values just become negative, but the x values remain the same. So let's go ahead and plot some of these points. So this is x value of 9, but now y value is negative 2. This one is x value of 3, but the y value is negative 1. And this one is an x value of 1, and the y value is still 0 because, well, negative of 0 is still 0. And you would connect those points. Essentially all you're saying is it's been flipped about the x-axis. Try to make it as accurate as possible, but you know that with logarithms, it's very difficult to make it super accurate. So this is as good as I think. As long as you also label your vertical asymptote, I think that's all you really need to be concerned with. So the green curve is y equals a negative log base 3 of x, or in other words, log base 3 of 1 over x. We finally graphed that. For the final example for graphing using transformations, let's go ahead and take a look at y equals log base 5 of x cubed. Again, I want to get it in terms of its base function, in other words, log base 5 of x. And the x cubed is what's screwing me up, but I know I have a property of logarithms where I can take that exponent and pull that out front. So I'll go ahead and do that. This is the same thing as graphing y equals log, or y equals 3 times log base 5 of x. And now I see, oh, that's just going to be basically the log base 5 of x function, but 3 times as high, so stretched by 3. And that's by a factor of 3. Actually, not just by 3. So let's go ahead and do that. Let's first draw the base graph, log base 5 of x. To do that, I'll go back to a base graph for a logarithm here, and in this case I have log base 3 previously, so what I'll do is I'll adjust this and make it log base 5. The shape will be basically the same. And as you can see by my manipulations here, that this is basically the same shape. It's log base 5 of x now. Again, all logarithmic base functions go through 1, 0. And then you have stuff like this where if x was 5, then the output would be 1. If x is 25, the output would be 2. Some students ask, do I have to put 25, 2 on my graph? And the answer is only if you have enough room on your graph. If you don't, then don't bother. Now remember, we want to graph y equals 3 times log base 5 of x. What that's going to do is take each of these outputs and multiply them by a value of 3. So this height of 2 will now be 3 times taller at a height of 6. So it'll go through 25, 6. And this height of 1 will be 3 times taller at a height of 3. So 5, 3. And this height of 0 will be 3 times taller, but 3 times taller than 0 is 0. And actually, it turns out the same thing is true on the back side, or the between x equals 0 and x equals 1, that these x values down here will also be 3 times lower, which doesn't make a huge difference on the graph, so I'm not really super concerned about that. I doubt that most instructors would be that concerned about it, but I'll show you kind of the effect of it, just so you know. But then you just connect these points up, curve down like this, and actually on the other side of this, it just drops a little bit faster, that's all. But it still eventually hugs the vertical asymptote, so it's not a huge deal. And this is a graph of y equals 3 log base 5 of x. There's a lot of other shifts and translations you can do, so you can move things up by 3 units or to the right by 3 units. In fact, I do want to do one of the ones to the left or the right by so many units. So let me do one last example. To make my life a little bit easier, I just still kept the same base, log base 5, and I still kept the same power. Now, using manipulations here, I know that this is the same thing, y equals log base 5 of x plus 7 being cubed plus 1, is the same thing as saying, well, I could take that exponent and move it out front. Notice that exponent is on this picture of x plus 7. That's why I can move that exponent out front. It's because it's affecting that entire picture. So I'll move that exponent out front, so it's a 3 times log base 5 of x plus 7. And then on the outside I still have this silly plus 1. So basically, we are going to graph, first of all, log base 5 of x. Then we're going to stretch vertically. So reading from left to right, that's how I always graph shifts and translations, or translations. I read from left to right, so we're going to stretch vertically by a factor of 3. But we've actually, that was my last example, that's why I'm using this. We already have 3 times log base 5 of x, so we're going to start from there. And then we're going to shift, well, let's see, it's plus 7 on the inside. Remember, on the inside it's always opposite of what you would think, so instead of going to the right 7, this will go to the left 7. So shift 7 units left. And then finally, that plus 1 on the outside is shift 1 unit up. So let's go ahead and do that using our last graph. In our last problem, we had already graphed log base 5 of x, and then we multiplied it by 3. So we had 3 times log base 5 of x. Now we're going to shift all of this over 7 units to the left. The way you do this is you grab the vertical asymptote, and it's super important that you move the vertical asymptote first. So you move that vertical asymptote 1, 2, 3, 4, 5, 6, 7 units over. So here's the new vertical asymptote. So you can kind of ignore my old vertical asymptote because it's been moved to x equals a negative 7. That's the equation of that vertical line. And then you redraw all these points. So let me go ahead and redraw these points. I'll do this in red. So this point that was going through 1, 0 has been shifted 7 units over in the x direction. So subtract 7 from the x value and you'll be right over here at, well, I'll point an arrow to it because it's going to be kind of messy, at negative 6, 0. And this point that was at 5, 1 will be shifted 7 units over to the left. So 5 minus 7 will be a negative 2, 1. So we'll be over here at, I'll point an arrow, negative 2, 1. And if you really want to be super exact, oh wait, I'm graphing the wrong one. That last one is not correct. Let me just erase that out. Sorry about that. We're graphing the blue curve. We're shifting the blue curve. So let me go ahead and shift that blue curve really quickly. All right. The blue curve, we're going to shift that point 5, 3 to the left 70. So it'll be actually at negative 2, 3. And I almost messed that up. So negative 2, 3. And then finally, this point that was at 25, 6 will also be shifted over to the left 7 units. And that'll be 25 minus 7 is 18, 6. Otherwise, you just connect those points up to make essentially the same graph, the same looking graph. Now, something that I've had students ask in the past, they've asked me, well, do I need to make sure that I label like y-intercepts and x-intercepts? The answer is no. It's really difficult to do that with logarithms. The idea with the logarithm is to get the basic, actually, the idea with any base graph really is just to use the base graph to get a basic idea of what the graph looks like. Nothing else. You don't want to get too fancy with a base graph. I mean, you want to be somewhat exact like I am right now, but you don't want to worry about finding y-intercepts, x-intercepts, because it just starts getting real messy. main thing you do is you have to label at least 2 points, and you have to keep your vertical asymptote in there. Finally, so that was shifted over. So this red curve actually represents y equals 3 times the log base 5 of x minus 7, or I'm sorry, x plus 7. Now we just have to add 1 to this curve, which means shift everything up by 1. So let me go ahead and do that. And I'll do this in blue. So I just removed the second to last curve. So I'm going to move all these points up just by 1. So that point went up by 1, this point went up by 1, and this point will go up by 1. Let me just relabel these. This is the point 18, 7 now. This is the point -2, 4, and this is the point -6, 1. Otherwise, again, just connect up these points. Get a nice, beautiful curve here. Again, it'll hug the vertical asymptote. And I have to go from right to left when I graph just because it's very difficult otherwise for me to do this freehand. Okay, so that last graph is the final graph. Y equals 3 log base 5 of x plus 7, finally plus 1. Let's talk about how we got that. We have this base graph in black. We stretched it by a factor of 3, moved it to the left 7 units, and then up 1 unit. That's how we got to that final answer. Usually students like to erase all the intermediate answers, so all the stuff in between. They just like to leave the first and the last graph. I don't really care if you're one of my students whether you do that or not. In fact, often it's nice to keep all graphs in there. It just looks a little bit better. So, well, actually, let me clarify. It doesn't look better, but it is better so I can see shifts and translations, kind of understand what you did. But this is the basic that you'll need. You'll need at least 2 points labeled and the vertical asymptote. All right, that's it for graphing translations of logarithmic functions. And actually, that's it for logarithms.